Welcome to the first lesson in the Sequences and Series unit of Pre-Calculus 12. We're going to start by taking a look at arithmetic sequences, which are sequences you've actually, in some cases, experienced before when you were looking at linear equations and linear patterns. So there may be some pieces that look familiar about these. So we're going to start with some vocabulary. A sequence is an ordered list of elements, and when we're talking about elements of a sequence, we call them terms. An arithmetic sequence we call it arithmetic, even though the spelling is the same as arithmetic. So in an arithmetic sequence, it's a sequence where the difference between any two consecutive terms is constant, which essentially means if you list the numbers in the sequence, it is either going up or down by the same number each time. We call this a common difference, the number that we're going up or down by each time. And it can be either positive, which is where you are going up, each term is bigger than the one before, or negative, where you're going down. So the common difference can be found by doing a small formula, t sub n minus t sub n minus 1. There's a lot of subscripts there, so what does that actually mean? Basically, what it's saying is that you can find the common difference by taking any two terms and subtracting the earlier term from the later term. Okay? So to find the common difference, you take any term and subtract the term before it. We can define a general term for a sequence. And that's an expression, or actually an equation in this case that we use, that directly will compute any term of the sequence. So it's a way using variables to be able to find any term of a particular sequence. All of these vocabulary words are pretty abstract, so let's take a look at an actual arithmetic sequence and see how they work out when we are looking at this sequence. Okay, so we have an arithmetic sequence, 5, 9, 13, that just kind of keeps on going. Okay, so the common difference we can find by subtracting any of the two any pair of numbers as long as they come in a row. So we always do the later one minus the earlier one. So 9 minus 5 gives us 4. 13 minus 9 would also give us 4. And if we were to continue the sequence, any other two terms in a row would subtract to give us our common difference. These numbers are going up by 4 each time. So let's take a look at what the terms of the sequence would be. So our first term we're going to call T1. We call it T1 because it is the first term. T2 is the second term, T3 is the third term, T4 is the fourth term, T100 would be the 100th term. And we're going to call Tn the nth term. So it's the term that comes in the nth position. So the little numbers down by the side of the terms just indicate what position in the series the number is in. So we've got 5, 9, and 13. What comes next? Well, we're going up by 4 each time, so I'm just going to add 4 to 13, and I get that T4 is 17. Now I have to find the 100th term. Now, I could find the 5th term, and then the 6th term, and then the 7th term, but I honestly don't think I feel like adding 4 that many times. It's going to take a long time. So what I'm going to do instead is I'm going to try to look for a pattern that will enable me to find T100 without having to do all of that addition. So we've got 5. So that's our first term. Our second term is 5 plus 4. Our third term is 5 plus 4 plus 4. So what I'm going to look at just the number of times I've added 4. So here, to find the second term, I've added 4 one time. To find the third term, I've added 4 two times. Let's see about finding the fourth term. So if I do 5 plus 4 plus 4 plus 4, because I had 5 plus 4 plus 4 was 13, so I'm just adding 4 one more time, you notice that I have added 4 3 times. Okay, so now what I'm going to do is I'm going to try to look at the number of times I've added 4 and associate it with the little subscript number. So what we have here is we have for T2, I've added 1 time. I've added 4 1 time. For T3, I've added 4 2 times. For T4, I've added 4 3 times. For T5, I would have added 4 4 times. For T6, I would have added 4 5 times. So what I'm noticing is that the number of times I had to add 4 was 1 less than the term number, than the number that gives me which term it is. So if I have to find T100, that means that I should be adding 4 99 times. So this would be 5 plus 4 plus ... plus 4. So when I put an ellipsis in the middle, that means that I'm adding 4, and I'm going to indicate that this is 99 times. So if I'm adding 4 99 times, thankfully, we have multiplication that we can use to simplify that. So 4 times 99 is 4 less than 4 times 100. So that would be 396. And if I add 5 to that, I get 401 for my T100 without having to add all those 4s. Well, that was great. What if I wanted to find T1000? Well, I guess I'd be adding it 999 times. So this allows you to calculate terms pretty quickly. So what we're going to do is come up with a general formula that we can use on any sequence, because for a different sequence, the common difference might not be 4. We might not be starting with 5. So what we notice is that we take our first term. For T2, we've added the common difference once. For T3, we've added the common difference twice. For T4, we have T1 plus the common difference, whatever it is, doesn't have to be 4, 3 times. So that would be T1 plus 3D. And again, I'm looking at this number and I'm noticing that 2 is 1 less than 3. 3 is 1 less than 4. So how would I write it? So for the 100th term, let's jump down a little before we try to write out how we would work out T100. Well, we're adding 99 times. So for any sequence, because we've changed the common difference, it's going to be T1 plus 99D. Okay, so whatever our first term is plus 99 times the common difference should give us the 100th term. So for the 100th term, we have to add the common difference 99 times. So for the nth term, how many times do we have to add the common difference to T1? Well, n can be anything. It's always got to be, but we're going to add the common difference 1 less than the position or the nth of the nth term. So the way we would write that is n minus 1, 1 less than the number of the term. This gives us the formula for the general sequence of an the general term of an arithmetic sequence. T sub n equals T1 plus n minus 1 times d, where T1 is the first term, n is the term number. So when you're talking about the term number, we're thinking first, second, third, all the way up to the nth. So that's our n, is which position is it in, how many numbers in to our sequence is it. D is the common difference, which is how much it's going up or down by each time. And T sub n is the nth term, which is the actual value of that nth term. So if I'm looking at T12, it's not 12, it's whatever the 12th whatever number the 12th term is of that particular sequence. And we can use these formulas to figure out all kinds of things about arithmetic sequence and sometimes solve some problems that wouldn't be so easy without the formula. Okay, so for the first two, we're just going to explore the sequences and try to look at some of our variables that we're using. So we're going to find T1, the first term, and D, the common difference for the first two for the sequence, and then write the general term. So if we look here, the first term, that's usually pretty easy. T1 is 3, first number that pops up. The common difference, we can subtract any two terms. I'll do 8 minus 3 because they're smallest, and I get D equals 5. So now I'm going to write the general term. So T sub n equals 3 plus n minus 1 times 5. I'm just using the formula right up there, this Tn equals T1 plus n minus 1 times D, and I'm replacing T1 with 3, and I'm replacing D with 5. And if you want to, you can write out the formula each time. It will help you memorize it, but you will be given the formula for tests, so you don't have to have it perfectly memorized. Okay, so now I'm going to simplify this. So I'm going to expand the brackets here properly. 5n minus 5. 3 minus 5 gives me minus 2. So this simplifies to Tn is minus 2 plus 5n. You don't necessarily have to simplify each time. One of the things you might find interesting is this looks quite a lot like a linear equation. And in fact, if you're doing arithmetic sequences, your general term should always come out looking something like a linear equation, like the kind you would use to graph a line. Okay, so next one, T sub 1, again, pretty easy. We just look at the first term. It's negative 2.5. Common difference, I'm going to do negative 3 minus negative 2.5. And that's going to give me a negative 0.5, or negative 1/2 if you prefer fractions. So my T sub n is negative 2.5 plus n minus 1 times negative 0.5. And we can simplify that if we would like to negative 2 minus 0.5. N. Doesn't look as instantly like a linear equation, but if we were to switch that to a negative 1/2, we tend to use fractions, might be a little bit more recognizable. Okay, moving on. One of the things that you will encounter quite a bit in the sequences and series unit is word problems. And the nice thing about these word problems is that you're generally trying to associate elements of a sequence to what you see in the problem. So since we're looking at arithmetic sequences, what we're going to be looking for as we read through the problem, we're going to be looking for T1, we're going to be looking for D, we may be looking for N, and we may be looking for T sub n. So we may be looking for the value of a later term that's not the first term. Okay, so let's read the problem. Children between 3 and 10 grow about 5 centimeters per year. Suppose a child is 70 centimeters at age 3. So since we're looking at between 3 and 10, and we're starting at age 3, this is going to be our T1. Okay, so which one is it? Is T1 3 or is T1 70? We have to figure out what we're making a sequence of. So let's read further into the question. Write the general term you could use to estimate a child's height. So our sequence is going to be of heights. So it looks like our T1 is going to be 70 centimeters between the ages of 3 and 10. So we can look back here. Children grow about 5 centimeters per year. So we're going up by 5 every year. That's going to be our D, or our common difference. So if we know T1 is 70, D is 5, then we have T sub n is T1 plus n minus 1 D. I don't require you write this out, but if you want to, it can be helpful just so that you do your substitution properly. So you get equals 70 plus n minus 1 times 5. And then if we want to go ahead and simplify that, we get T sub n equals 65 plus 5n, and we can use that to calculate. So next, we're being asked how tall will a child likely be at the age of 10? And this is actually going to take us into one of the more interesting and challenging aspects of sequences and series, which is how do we count how many numbers there are properly? So the question here, we're starting at 3. 3 is our T1. So we're going from 3 to 10. So we want to know how many ages the child is going to hit, starting at 3 and then ending at 10. Okay, so some people like to say, well, 10 minus 3 is 7, so 10 should be T7. That's actually not correct. Let's list out those numbers. We have 3, 4, 5, 6, 7, 8, 9, and 10. And if I actually count how many there are, we have 1, 2, 3, 4, 5, 6, 7, 8 numbers between 3 and 10, despite the fact that 10 minus 3 is 7. What's going on? We have to think about whether we're trying to find the difference between two numbers or how many numbers, including the first number, there are. So when we subtract, we're not counting the first number as like a 1, we're counting it as a 0. So what we want to do is we want to count inclusively. So if you want to count starting at 3, ending at 10, how many numbers are there? It's always going to be one more than the difference between them. So you have to be really careful about that. So at the age of 10, it looks like what we're really looking for is finding T8 of this sequence. So T8 is going to be 65 plus 5 times 8. So 5 times 8 is 40, and 40 plus 65, this gives us 105. This being a word problem, we have to actually answer the question. Okay, so the child will be likely 105 cm tall. Okay. Next problem. This is a question that involves words, but it's really a question that's going to ask us to use some of our numerical values to determine how many terms this sequence has. So again, we have the option of writing them all out, but if I'm counting down by 5s, if I have to write out all the numbers from 981 to 551 by 5s, that is going to take me an awfully long time. So let's see if we can use our formula for the general term. So Tn equals T1 plus n minus 1 d to figure out how many terms the sequence has. So we know T1 is 981. We know d is -5. What we want is we want to figure out, we're stopping at 551, so we want to figure out really what the term number of 551 is, so how many terms it is to get to 551. So what we're going to do is we're going to label Tn equals 551, and n is going to remain a variable. That's what we're actually trying to find, is how many terms there are. So I'm going to substitute these in. I get 981 equals 551 plus n minus 1, we can't plug that in because it's a variable, times d, and d is -5. So generally with these, whoops, I think I got those backwards. Let's switch those. You'll find I make the odd mistake. We have 981 on this side and 551 on that side. We want to sub Tn for Tn and T1 for T1. Okay, so now I usually try to just get all the numbers on one side first before dividing. So I'm just going to subtract 981 from both sides, which leaves me with -430 is n minus 1 times -5. And then I'm going to divide both sides by -5, which gives me 86 equals n minus 1. Then adding 1 to both sides, I get that 87 is n. So the sequence has, let's interpret that, the sequence has 87 terms. So we would have had to write out 87 numbers if we had tried to do it by hand. That would have taken some time. Okay, last example. So the fourth term of an arithmetic sequence is negative 29, and the eighth term is negative 13. First question is, what is the common difference of the sequence? So I'm just going to start by writing out my known information. So I know that T4, my fourth term, is negative 29, and I know that my T8 is negative 13. So if I look at my formula, and I'm just going to write it right up here so we can have a good look at it. So T sub n equals T1 plus n minus 1 times D. I notice that I have 4 pieces of information. And usually, if I'm trying to solve an equation, I need to have only one variable that's left. So I have 2 different pieces of information for 2 different terms. So, and I notice that I have 2 pieces of information about each of those terms. So I know what the term number is, and I know what the value of that term is. So I know T sub n, and I know n, but I don't know T1 or D. So what I'm going to have to do is I'm actually going to have to write down 2 equations. So let's write down one for T4. So T4 is T1 plus, well, we know for this term n is equal to 4. So that's going to be plus 4 minus 1 times D. Now I'm going to replace T sub 4 with its value, which is negative 29, and simplify a bit. So I get negative 29 is T1 plus 3D. Now I'm going to do the same thing for T8. So the eighth term is T sub 1 plus 8 minus 1 times D, so 1 less than the eighth term times the common difference. I'm going to replace T8 with negative 13, so I get negative 13 is T1 plus 7D. So now I'm left with 2 equations with 2 variables. And some of you may remember from Math 10 and possibly from Math 11, that we can solve a system of 2 linear equations using 2 different methods, substitution and elimination. For this one, I am going to use elimination, but sometimes substitution is the better bet. The reason I'm going to use elimination is because I notice the T1s are the same, so all I have to do is subtract one equation from the other. And I'm going to make it simple. I'm going to put the one with a bigger number for D up there. So I'm going to have negative 13 equals T1 plus 7D. I'm going to put underneath it negative 29 equals T1 plus 3D. And I am going to go ahead and subtract. So I've got negative 13 minus 29 gives me a positive 16. And that T1 minus T1 goes away. 7D minus 3D is 4D. So I've got 16 equals 4D, and then I get D equals 4. So I found the common difference. I have answered my question. And sometimes I like to do a common sense check here and look and say, well, if D is 4, that means the fourth term we're going up, so that means the fourth term should be smaller than the eighth term, and it is in fact. So that worked out logically. One thing you might notice is that, well, if you look at that number, well, the difference in the terms, if I had just done negative 13 minus 29, I get 16. And if I do 8 minus 4, I get 4. And then I divide 16 by 4. So there is a shortcut. And what that shortcut is, if you have 2 terms, you can do TB minus TA over B minus A. And that's going to give you your common difference. So basically, if you have any 2 terms, you subtract the values of the terms, starting with the later one to the later one minus the earlier one, and then the difference in their position, and you divide by that, and that should give you the common difference. Let's determine the general term now. Well, it doesn't really matter which T sub n we use to find T1, so I'm going to use the first equation. So I have negative 29 equals T1 plus 4 times the common difference, plus 3 times the common difference, which we know now is 4. So I can just go ahead and replace that. And then solving, we get T1 equals negative 41. So my common difference, T sub n, is negative 41 plus n minus 1 times 4. And I don't necessarily have to simplify it. So now, if 31 is a term in the sequence, what is its position? So we're looking for n. I can use what I have just calculated. So 31 is going to be my t sub n, and we're looking for the n for that particular t sub n. T sub n and n come in pairs. So I'm going to use 31 equals negative 41 plus n minus 1 times 4. Adding 41 to both sides, I get 72 is n minus 1 times 4. Dividing by 4, I get 18 is equal to n minus 1. And then adding 1, I get n equals 19. And you can find any homework, additional exercises on OneNote.